In this video, we explain the storage system that works underneath the Caretaker in the project house. It is very similar. In fact, it is in many respects a copy of the system working in Git. As in Git, the normal user does not really need to understand all this in order to use the program. In fact, for a first introduction to the Caretaker in the project house, it may even be a good advice to skip this altogether. There are two parts. First, a brief look into the principles of how Git monitors a project with an attached Git repository. Second, we explain the SHA-1 storage system that works in the Caretaker in the project house. One challenge for the management of a single project is a control over its history. But in a file system, a project has no history. It is always in its most current state. All previous changes and states are lost during the process. This particular problem of project management is tackled by a group of management tools often called version control systems. And the most popular at the moment, that has become a standard for programmers, is Git. Git is open source and freely available. On Linux distributions, it is installed by default. Git was originally developed as a development tool for the huge Linux project itself. It works by attaching a so-called repository to a project, where previous project states are kept. And the project history does not have to be linear. Instead, it is possible to work on different branches for the same project. It also is designed for distributed development in the sense that many people work independently on the same project. And there is no central repository. Each developer has a full local copy, and the different developments can later be merged again. There is no default GUI for Git, although there are several ones available. The program itself is just a command, namely Git, to be used on the command line. It has a wide and altogether powerful range of functions, but that also means that it has a steep learning curve and that this tool does not seem to be widely used by other digital content producers and programmers that are used to the command line. Part of Git's success is its whole ecosystem and vibrant community. On dedicated places like GitHub, project developers can collaborate, present and share their projects. Let us briefly review how Git adds a very flexible history to a project. Given our file system with some projects, let us pick one that we start to monitor with a Git instance. Suppose the project resides under its home directory called My Process. The active or so-called working file tree with the project content resides in the red-colored area. We open a terminal, move into the home directory, and then call git init. That creates a so-called repository, a hidden folder named .git, containing the structure of a very clever storage system. The folder is hidden and it shouldn't be touched directly. The only correct way to use the repository is by git commands. An important one is git commit, which makes a backup of the working tree and puts it into the repository. Actually, it does not make a snapshot of the whole tree, but only a previously selected part. But that is not important here. Each subsequent time a commit is made, a separate copy is stored in the repository and an unlimited stack of commits is generated. But the history of a Git project is not only one-dimensional. It is possible to create different branches and develop in different directions and switch between these branches. With a git checkout command, the content of a particular branch turns into the new active one by restoring the last commit of the particular branch as a current working directory. All this makes the Git repository a powerful tool for project development. But it is not an easy one. Everything has to be done by commands with a steep learning curve. Later on, we will try to show that the Caretaker in a project house provides the same power much more elegantly and intuitively. and not just for one, but for any number of projects you are working on. We refer to Git because it is a well-established and widely known tool. It helps us explaining the new Caretaker in a project house, but also because we stole the core design of Git to implement the Caretaker in a project house. The Git community itself uses a distinction between the porcelain for the Git user and the plumbing under its hood. This core structure and machine, where Git derives all its powerful features from, is what we call the SHA-1 storage system, a content-addressable storage system using the secure hash algorithm 1. The SHA-1 storage system design is pretty much the plumbing and the common machinery for Git and the Caretaker in a project house alike, whereas the porcelain and the user experience is completely different. An understanding of this plumbing is not necessary for any of the two programs, but it makes some seemingly arbitrary-looking things really plausible and consistent. A numeral is an expression for a number. The global standard nowadays is the decimal or base 10 numeral. Expressions made of decimal digits, the 10 characters 0, 1, etc. to 9. In the world of computers, numerals are often not base 10, but base 2 or 8 or 16. So a hexadecimal or base 16 digit is one of 16 characters, namely the 10 decimal ones and the characters A, B, C, D, E, and F. A hexadecimal numeral is a string of hexadecimal digits. In our context, we will concentrate on the hexadecimal numerals, which are made of exactly 40 hexadecimal digits. We call these hex 40 numerals. Each hex 40 numeral stands for a number, and that number can be written in standard decimal notation. Our example hex 40 numeral 6C79, etc. is a very big number, which is 6192, etc. as base 10 numeral. One important thing here to understand is that there are a lot of different hex 40 numerals. Their number is so huge that there is no risk to choose identical numbers when we make random choices. In any selection of say 10 or 100 or even a million hex 40 numerals, it is practically impossible that two of them are the same. This is an important statistical fact that we need to understand for the remainder of this video. The SHA-1 is a function that takes a file or a string and returns a hex 40 numeral. For example, if you take the line "Hello World," SHA-1 returns the numeral 47A0, etc. This value is the same for the string and any file containing this string. So if I take the file named hello.txt containing hello world and compute the result, it would be 47A0, etc. The name of the file does not matter. If the file would be named, say, greeting.md with hello world in it, the output would still be 47A0, etc. By the way, if you are on a Linux machine, the SHA-1 is already built in and is called SHA-1 sum. And to compute the hex 40 numeral of a hello.txt file, you can open a terminal and call SHA-1 sum hello.txt. The SHA-1 has a couple of very useful features that makes it very interesting for our purposes. First, it is a proper function in the sense that it is deterministic. Equal files or strings produce the same hex 40 value, always and on every machine. Second, it is really fast. On a fairly contemporary machine, the time to compute the values for several, even big files is almost not noticeable for a human. SHA-1 turns arbitrarily big files into 40-character numerals, which are relatively tiny strings. This is a typical feature of a so-called hash function for storage applications, and each hex 40 value then works as an address under which the file can be stored. Third, it is quasi-unique. A function is unique or injective in proper mathematical jargon when two different inputs always produce different results. To be precise, the SHA-1 cannot really promise that. When an actually infinite amount of different files is mapped to the finite amount of hex 40 numerals, there will always have to be many different files that do have the same value. But since the finite amount of different hex 40 numerals is astronomically huge, remember a decimal with 49 digits, it is statistically really safe to assume that this case will never occur in real life. It will practically never happen that we are confronted with two different files with the same SHA-1 value. So the function is not strictly unique, but quasi-unique at least. 4. It is quasi-irreversible. If a file or string has a certain hex 40 value, and you only have the hex 40 value, then the only way to find out about the original file is to test all the files there are, until the result is a match. And that is infeasible. It is pretty impossible to draw conclusions or even to reconstruct the original input file or string just from its hex 40 value. Even if the difference between the two files is very small, the hex 40 value will be very different and does not show any similarity at all. The last property in particular makes the SHA-1 especially useful for cryptographic applications, and that was its original idea in the first place. Recently it turned out, however, that the SHA-1 is not so secure, that it can be attacked and should therefore be replaced by its improved successor SHA-2 and SHA-3. But for our purposes, the last property is not important, whereas the others are very much. Therefore SHA-1 is still used in Git and other systems, and it will continue to be used, not for security, but as a hash function for content-addressable storages. Let us emphasize an important consequence from the properties of SHA-1. Suppose there are two files, F1 and F2, and their according SHA-1 values are H1 and H2 respectively. Then there are two things we can be sure of. If the two hex 40 values H1 and H2 are different, then the files F1 and F2 are different too. And if H1 and H2 are equal, then the files F1 and F2 are also equal. Let us now introduce a powerful SHA-1 storage, as we call it, the irredundant content-addressable storage system for files and entire file trees. We will soon see what irredundant and content-addressable means here, and why irredundancy is so very important for project management. Consider this simple file tree made of 4 folders named A, B, and C twice, and of 8 files. All are either text or JPEG files. Let us now compute the SHA-1 value for each of the 8 given files. Let these be the according results. Let us attach the hex 40 value to each file in the tree image. These values don't tell us anything about the file content, according to the quasi-irreversibility of SHA-1. What we do know that files with different hex 40 values have different content, and files with the same hex 40 values have the same content. Consider the two files with the same name a.txt. We don't know their content, but we do know that both file contents must be different, because the hex 40 numerals FBEB and FB9F are different. On the other hand, there are two files with different names, DJPEG and FJPEG, but the same SHA-1 value FD9D, so their content must be the same file, which means the same JPEG picture. We can also generate quasi-unique hex40 values for directories and entire file trees. We do this in 2 steps. First, we translate the file tree into a JSON object, and then we compute the SHA-1 value of the string representation of this JSON object. JSON values are simple and special data structures that are standard format in web technologies. A JSON object is a special JSON value, namely a series of key-value pairs. The recursive definition for the conversion is this. That way, every file tree is represented by an expression, a JSON object. Accordingly, our example tree converted into a JSON object looks like this. We added some extra white space and indented the subvalues to make the structure more readable. The default representation is actually without this extra white space. Anyway, this JSON object, taken as a string or put into a file, is then a proper input for the SHA-1. The hex40 value that comes out is 932B, and this is then defined to be the SHA-1 value for the original file tree under A. Note that the properties of the SHA-1 for strings and files are inherited. In particular, the SHA-1 for file trees is also quasi-unique. As a consequence, we can always safely assume that 2 file trees with the same content have the same hex40 value, and vice versa. If 2 file trees have the same hex40 value, they must have equal structure and content. Let us now show how we build the SHA-1 storage and how we store and retrieve files and entire file trees. Let us take our example file tree again. So far, we computed the SHA-1 values for its 8 files and the SHA-1 value for the entire file tree under A. This is a table that summarizes our results. We now turn around this table and make the hex40 values the arguments or addresses referring to either file content or JSON objects. This gives us the following hash table. Note that there is one hex40 value, FD9D, that points to 2 identical file contents, that of DJPEG and FJPEG. Now we implement our SHA-1 storage. We create a folder, say .storage, and for each entry of our hash table we create a file that has according content in it and is named after its own SHA-1 value. We can now say that our entire file tree is stored under 932B, the address for the JSON object of the file tree under A. This is actually a proper storage for our file tree. We can prove this by reversing the process and recover the original tree again, just from the single hex40 value 932B. In the first of 2 steps, we look up the file content of the file named 932B. Out comes a JSON object that provides us with the structure of the whole file tree. We can identify folders and files, all their names are present here. So we can build a file tree at the desired place with exactly this structure. And for each file we have a hex40 numeral referring to its content. So in the second step we retrieve for each file the content of this file by looking up the content under that hex40 address and copy the content to the according file in the file tree. That's it. We were able to reconstruct the original file tree again. And of course, we can now add many more entire file trees to the storage, more content to the .storage folder. We just need to remember the hex40 address for the file tree, and then we can retrieve it again at any time. And that is what happens each time a commit is done in Git. Essentially, a file tree is stored into the SHA-1 storage. Actually, things are a bit more modified in the real SHA-1 storage. In our example, we have 8 items in the .storage folder. But when this storage is in use, this folder will fill up very quickly and there will be a huge amount of items in it. To make this a bit more compact, all these items are distributed on buckets and sub-buckets, each bucket being a folder of, say, 2 hexadecimal digits. So, for example, the item addressed 10A7E9, etc. would first be put into the folder named 10, then into the subfolder named A7, and there it would be stored under the address E9, etc., a name that now has only 36 characters instead of the original 40. That way, the amount of items in the .storage folder is limited to maximally 256 folders, and everything is a bit more compact. But all that doesn't change the basic concept of the SHA-1 storage. Also, Git is actually a bit more sophisticated than the SHA-1 storage depicted here. Also, Git does not use JSON, but another text format. And it does not transform file trees into deep data records. Instead, every directory is flat and only holds the items in the directory itself, and the subdirectories become items on their own, stored under their own hex 40 address. There are pros and cons to this design, but we neglect all this here. It wouldn't change the basic idea and argument. One important question does remain, however. What is all this good for and how does it make sense? Let us revise what we built so far. On one hand, we have our file tree, or any amount of file trees. On the other hand, we have our SHA-1 storage that holds this file tree, or any amount of file trees. There's a 1-1 correspondence between these two sides in the sense that a file tree can be stored and retrieved again without any loss of data. But why should I want to use such a storage in the first place? It has some information, but is more difficult to comprehend due to all these alienating hex 40 addresses. Well, the huge difference is that our file tree is redundant, whereas the SHA-1 storage is truly irredundant. Recall that we had 2 files in our file tree with the same content, DJPEG and FJPEG. In the file tree, these 2 files use twice the space than each one of them. In our SHA-1 storage, both files are just stored once under the address FD9D. Any 2 equal files and any 2 equal file trees are only stored once. So imagine a project monitored by Git, where we made, say, 10 commits so far. That means that we store 10 file trees, but usually 2 subsequent commits have a lot of files in common and differ only in a fraction or small part of the file tree. When we would store each commit just by copying entire file trees as such into the storage, we would end up with about 10 times the storage space compared to a single commit. But our SHA-1 storage saves equal files only once. So a file that occurs in each commit is not stored 10 times, but only once. In effect, the 10 commits don't require 10 times the storage space of a single commit, but may be not much more than a single commit itself. If we would make commits by simple file tree copies, we would and should hesitate each time we make a commit, because we blow up the storage space each time. But in the SHA-1 store, there is no trade-off between safety and wasting storage space. If not much has changed between 2 commits, then there is not much new storage space occupied. There is no reason anymore to be parsimonious with commits and backups in the SHA-1 storage. By using content-addressable storage, irredundant file and file tree storage is possible, and that is mandatory for a space-efficient backup system. Similar to Git, the SHA-1 storage is part of the plumbing, and the Caretaker and Project House user will never have to deal with all this, really. Instead, there are only buttons to click in the Caretaker GUI, and all this storing and retrieving happens under the hood. It does help to understand, however, that it is an irredundant storage system in the just mentioned sense, so that users know that there is no trade-off between making a commit or backup and wasting storage space. If you are a JavaScript programmer working with Node.js, you can use the SHA-1 storage as an independent tool. It is part of the TOF.js project and can be installed as an npm package.